Welcome to my 60-second tutoring session in A-level chemistry. In this video, I'll explain the influence of pH and the presence of auxochrome on the lambda max, bathochromic shift, hypsochromic shift, hyperchromic effect, and hypochromic effect. Please take a moment to watch my previous video where I have given detailed explanation about these 5 important parameters related to UV visible spectroscopy. That is, I have given explanation about lambda max, bathochromic shift, hypsochromic shift, hyperchromic effect, and hypochromic effect. And this video will provide you with a better understanding of this video content. Now, before I get on with the explanation, I'd like to give a brief overview about these 5 important parameters related to UV visible spectroscopy. Now, you'll be making use of the same absorption curve in order to understand the rest of the 4 parameters, that is bathochromic shift, hypsochromic shift, hyperchromic effect, and hypochromic effect. But this time you will be making use of the visible region whose wavelength ranges from 400 to 800 nanometers. We have already learned that lambda max is the wavelength where there is maximum absorption of radiation by the drug substance or the molecule of interest that is being analyzed. Now, what is bathochromic shift? Now, bathochromic shift, also called as red shift, is the shift in lambda max towards longer wavelength. So during bathochromic shift, you will find that there is shift in lambda max towards longer wavelength, that is towards the red region. So red region, you can see that the wavelength is more. So during bathochromic shift, there is shift in lambda max towards longer wavelength, that is towards the red region, and that is why this is also called as red shift, or this effect is also called as the red shift. Now, there are several reasons for the bathochromic shift. I have highlighted the 3 important points here. So bathochromic shift is caused due to increase in conjugation or the increase in the number of double bonds with increase in alkylation and also due to presence of auxochrome. These 3 are the major reasons for the bathochromic shift or the red shift. Now, these 3 points will be dealt in detail later on in the video. And what is hypsochromic shift? Shift in lambda max towards shorter wavelength is called hypsochromic shift. It's also called as blue shift. And hypsochromic shift, it is caused due to these 3 major reasons, and they are decrease in conjugation or double bonds, decrease in alkylation, and absence of auxochrome. Hypsochromic shift is also called as blue shift because, as you can see, during hypsochromic shift, there is shift in lambda max towards shorter wavelength, that is towards the blue region. That is why this effect is also called as the blue shift. So that is about the bathochromic shift and the hypsochromic shift. Now, moving on to the rest of the 2 parameters, that is hypochromic effect and hypochromic effect. Now, during hyperchromic effect, there is increase in the intensity of absorption. And what is hypochromic effect? During hypochromic effect, there is decrease in the intensity of absorption. Now, here you need to note an important point is that in case of hyperchromic effect as well as hypochromic effect, the lambda max remains one and the same. Only the intensity of absorption either increases or decreases. If the intensity of absorption increases, it will be hyperchromic effect. if the intensity of absorption decreases, it will be considered as a hypochromic effect. But the lambda max remains one and the same, as you can see from this absorption curve. While in case of bathochromic shift and hypsochromic shift, you can see that there is shift in lambda max either towards the longer wavelength or towards the shorter wavelength. So in case of hyperchromic and hypochromic effect, the lambda max remains one and the same. While in case of hypsochromic shift and bathochromic shift, the lambda max value changes. And how and why the lambda max value changes in case of bathochromic and hypsochromic shift, that will be discussed in detail later on in the video. Now one should familiarize themselves with these two key points. That is, the wavelength of the UV region ranges from 200 to 400 nanometers, and colorless compounds absorb radiation in the UV region. And the wavelength of the visible region ranges from 400 to 800 nanometers, and any colored substance will absorb radiation in this wavelength region. So one can differentiate a colorless compound to that of a colored compound in UV visible spectroscopy with respect to the absorption of radiation. A colorless compound absorbs radiation in the UV region, while a colored compound absorbs radiation in the visible region. So both colored compound as well as colorless compound absorb radiation. So only the wavelength of radiation changes or varies. I have considered phenylephrine drug molecule to explain the effect of pH and the presence of auxochrome on the lambda max of the drug molecule, and also see how the changes in pH produces bathochromic shift, hypsochromic shift, hyperchromic effect, and hypochromic effect in the phenylephrine drug molecule. Now in bathochromic shift, you see a shift in lambda max towards longer wavelength, and during hypsochromic shift, you see a shift in lambda max towards shorter wavelength, and during hypochromic effect, the intensity of absorption increases, and in hypochromic effect, the intensity of absorption decreases. Now before I explain the UV absorption spectra of the phenylephrine drug molecule under different pH conditions, I would like my viewers to have a thorough understanding about the structure of this phenylephrine molecule. When you observe the structure of phenylephrine, you find the presence of chromophore in the form of benzene ring and the presence of OH group, which is seen as a auxochrome. Now there are structural changes in the phenylephrine drug molecule under acidic and basic conditions. Now under basic conditions, the hydrogen atom that is covalently bonded to the oxygen atom of the OH group is removed in the form of proton, and as a result, you find the OH group is ionized, and it bears 3 lone pair of electrons, and in the side chain, you see the terminal methyl group is covalently bonded to secondary amino group where the nitrogen atom is bearing 1 lone pair of electron. So this is the structural change you observe when phenylephrine is dissolved in 0.1 molar sodium hydroxide solution, that is under basic conditions. Now what happens when you dissolve this drug molecule under acidic conditions? I mean when it is dissolved in 0.1 molar hydrochloric acid solution. Under acidic condition, you see that the secondary amino group in the side chain is protonated, and thereby the lone pair of nitrogen atom on the nitrogen atom in the side chain is lost or removed. And the auxochrome is retained as such, and there is no ionization of the auxochrome, that is the OH group, is intact without any ionization. So under basic conditions, you find 3 lone pair of electrons on the oxygen atom and 1 lone pair of electron on the nitrogen atom. While under acidic conditions, you find 2 lone pair of electrons on the oxygen atom and there is no lone pair of electron on the nitrogen atom in the side chain. Now let's study the UV absorption spectra of phenylephrine drug molecule under acidic and basic conditions. So the solvent used to induce the acidic condition is 0.1 molar HCl, and we have used 0.1 molar sodium hydroxide for basic conditions. Now the absorption curve that is highlighted in red is the one what you get under basic conditions, and the absorption curve highlighted in blue is the curve that is obtained under acidic conditions. So red curve represents the curve under basic conditions and blue curve represents the absorption curve under acidic conditions. Now we know that under basic conditions there are 3 lone pair of electrons on the oxygen atom and 1 lone pair of electron on the nitrogen atom in the side chain. And as a result, the strong auxochrome, that is the ionized oxygen atom, interacts with the chromophore, that is benzene ring, by resonance, and this leads to extension of the conjugated system. And as a result, you can see that the lambda max of phenylephrine under basic condition, that is in 0.1 molar sodium hydroxide, is 292 nanometers, and it produces bathochromic shift as well as hypochromic effect. You can see that the lambda max is shifted towards longer wavelength, that is towards the right side, that is at 292 nanometers, and also there is increase in the intensity of absorption. So under basic conditions, phenylephrine produces both bathochromic shift as well as hypochromic effect. So this is the curve what you get under basic conditions. Now what about acidic condition? Now under acidic conditions, lambda max of phenylephrine in 0.1 molar HCl is 272 nanometers, and this is due to 2 lone pair of electrons on the oxygen atom, and this produces HYPSOCHROMIC shift and hypochromic effect. You can see that the shift in lambda max towards shorter wavelength, and at the same time you can see the intensity of absorption is drastically reduced, as shown by the double-headed green arrow. So this double-headed green arrow indicates to what extent the intensity of absorption is reduced under acidic condition. So under acidic condition, that is in 0.1 molar HCl, the drug produces HYPSOCHROMIC shift as well as hypochromic effect, and under basic condition in 0.1 molar sodium hydroxide, it exhibits bathochromic shift as well as hypochromic effect. So it is just a matter of 1 lone pair of electron. You can see that 1 lone pair of electron makes a drastic difference in the absorption spectra. So when you have 3 lone pair of electrons, it leads to bathochromic shift and hypochromic effect, and with 2 lone pair of electrons, you see shift in lambda max towards shorter wavelength, resulting in hypsochromic shift, as well as the intensity of absorption also reduces. So here the hydroxy group, it functions as an auxochrome and it interacts with the benzene chromophore by resonance, and thereby it extends the conjugated system. resulting in bathochromic shift as well as hypsochromic shift. And the lone pair of electrons is released into the ring by resonance. And the mechanism for the delocalization of electrons on the oxygen atom into the benzene ring will be explained later in the video. Now I'll consider one more example to explain the effect of pH and the presence of the auxochrome amino group on the lambda max of the local anesthetic drug, that is procaine. And also let's see how the changes in pH produces bathochromic shift, hypsochromic shift, hypochromic effect and hypochromic effect in case of procaine drug molecule. So bathochromic shift, shift in lambda max towards longer wavelength; hypsochromic shift, shift in lambda max towards shorter wavelength; hypochromic effect, where you see increase in intensity of absorption; hypochromic effect, where the intensity of absorption decreases. So always remember these four parameters when you are trying to study the absorption spectra of any given drug molecule. Now let's study the structure of the procaine drug molecule, both under acidic as well as basic condition. Now the procaine molecule, it has a chromophore in the form of benzene ring, and a auxochrome is directly linked to the benzene ring by covalent bond. And here in case of procaine, it is the primary amino group, where you find one lone pair of electron on the nitrogen atom of the primary amino group. And in the side chain of the procaine molecule, you find ethyl group, that is two ethyl groups are covalently bonded to the tertiary nitrogen atom with one lone pair of electrons. Now under basic conditions, what are the structural changes you observe? Now under basic conditions, there are no structural changes. The primary amino group remains intact with one lone pair of electron on the nitrogen atom, and in the side chain, the tertiary nitrogen atom remains intact with one lone pair of electron. And under acidic condition, you can see that the primary amino group is getting protonated, and this results in loss of the lone pair of electron. So under acidic condition, the primary amino group is getting protonated, and thereby the lone pair of electron that was present on the nitrogen atom is no longer available. And therefore, under acidic condition, the primary amino group, after it is getting protonated, it no longer functions as an auxochrome. And even in the side chain, the tertiary nitrogen atom is also getting protonated. So these are about the structural changes that happens in the procaine drug molecule, both under basic condition as well as acidic condition. Now let's study the UV absorption spectra of procaine under acidic and basic condition. Now the absorption curve highlighted in red is the curve that is obtained under basic conditions, and the absorption curve that is highlighted in blue is the curve obtained under acidic conditions. So red curve under basic conditions and blue curve under acidic condition. Now under basic conditions, we very well know that the lone pair of electron on the primary amino group remains intact, and it interacts with the benzene chromophore by resonance, leading to extension of conjugation, and this results in lambda max of procaine in 0.1 mole sodium hydroxide to be 279 nanometers. and this leads to bathochromic shift as well as hypochromic effect. You can see a marginal shift in the peak towards the right side. There is a marginal shift and this leads to bathochromic shift, and there is a hypochromic effect. The intensity of absorption increases. Now the double-headed green arrow, it indicates the intensity of, that is the difference in intensity of absorption under acidic and basic conditions. Now under acidic condition, what happens to the primary amino group? The primary amino group is getting protonated, where the lone pair of electrons on the nitrogen atom is lost due to protonation, and under acidic condition, the primary amino group no longer functions as a auxochrome, and therefore there is a fall in the lambda max. So lambda max of procane under acidic condition is 270 nanometers, and this leads to hypsochromic shift. You can see the curve is marginally shifted towards left side. So there is shift in lambda max towards shorter wavelength, and at the same time we also see hypochromic effect. You can see a drastic decrease in the intensity of absorption as highlighted by the double-headed green arrow. So under basic condition, phenylephrine, that is procane, in 0.1 mole of sodium hydroxide produces bathochromic shift as well as hypochromic effect. And under acidic condition, procane in 0.1 molar HCl, it exhibits hypsochromic shift and hypochromic effect. And you can see it's just a matter of one lone pair of electron. How one lone pair of electron can influence the UV absorption spectra of a drug molecule. So one lone pair of electron, it leads to bathochromic shift and hypochromic effect, and loss of one lone pair of electron by protonation, it results in hypsochromic shift and hypochromic effect. So procane produces bathochromic shift and hypochromic effect in the presence of the auxochrome NH2, that is the amino group, and it produces hypsochromic shift and hypochromic effect in the absence of the auxochrome. So you did not take it literally. Absence of NH2 group means that after protonation of the amino group no longer functions as a auxochrome. And the auxochrome under basic condition, it interacts with the benzene chromophore. It releases electrons into the benzene ring by resonance, leading to extension of conjugation. Now about the mechanism involved in the extension of conjugation. Now I tried to explain the mechanism considering two chemical substances. One is para-nitroaniline, the other is para-nitrophenol. In order to showcase the effect of the auxochromes, that is OH and the NH2 group on the lambda max, or the influence of pH and the presence of auxochromes on the lambda max of two drugs that we have discussed so far. So when you observe the structure of para-nitroaniline, you can see that the amino group and the nitro group, they are para to each other, and you find one lone pair of electron on the nitrogen atom, and that is getting delocalized into the ring by resonance, and this leads to extension of conjugation. So as a result of extension of conjugation, you see bathochromic shift both in case of procane and phenylephrine. So extension of chromophore through the benzene ring by the auxochrome group, that is NH2. This happens by resonance. And same mechanism holds good even in case of para-nitrophenol. So in case of para-nitrophenol, you find the auxochrome group to be the OH group, where you find two lone pair of electrons on the oxygen atom, which is getting delocalized into the ring by resonance. And this leads to extension of the conjugated system. So the auxochrome OH is present in the phenylephrine drug, and the auxochrome, that is the NH2 group, amino group, is present in the local anesthetic drug procaine. So auxochromes like OH and NH2, it not only produces bathochromic shift or redshift by interacting with the benzene chromophore and extending the conjugated system between the chromophore and the auxochrome by resonance. At the same time, it also deepens the color. So aniline and phenol both are colorless, but due to the presence of the auxochrome, that is the amino group and the hydroxy group, you can see they are brightly colored. So here resonance plays a key role. It plays a key role in bringing about the extension of the chromophore through the benzene ring that is brought about by the auxochrome, be it OH group or amino group. Now the two examples that I have explained in this video has been taken from this book. That is a textbook for pharmacy students and pharmaceutical chemists by David G. Watson. I would strongly recommend this pharmaceutical analysis book for anyone who would like to further have a grasp over this particular topic. So I have tried to explain the influence of pH and the presence of auxochrome on the lambda max of phenylephrine and procaine in this video. I hope you enjoyed the video, and I'll meet you in my next interesting tutoring session.